Look at the sheer speed of modern innovation. We have artificial intelligence processing billions of parameters in seconds, and electric vehicles pushing 0 to 60 in under 3 seconds. But beneath all that cutting-edge processing power lies a surprisingly stagnant foundation. The vast majority of our modern world runs on a lithium-ion battery chemistry that hasn't seen a major structural overhaul in decades. This diagram shows the core architecture of a standard lithium-ion cell. It consists of two main functional ends, the anode on the negative side and the cathode on the positive side. Power storage relies entirely on moving particles between these 2 points. Because we still rely on this aging chemical design, the physical limits of our batteries have become a hard ceiling. Our power grids, our phones, and our transport networks are all restricted by the boundaries of this single architecture. The weakest link in this design sits right in the middle, the liquid electrolyte. This is a chemical fluid filling the empty space between the anode and the cathode. In the center gap, this fluid is a mandatory highway. Ions swim through the chaotic liquid, creating an electrical charge. But it has 3 fatal flaws. It is highly flammable, it restricts maximum energy, and the chemical soup degrades over time. To achieve longer-range vehicles and resilient green energy grids, engineers realized they couldn't just tweak the fluid. They had to eliminate this volatile liquid entirely. The solution is the solid-state battery. Engineers are replacing the chaotic liquid highway with a rigid, solid bridge made of specialized ceramics or glass. On the left, bubbling liquid. On the right, a solid-state lattice. This solid electrolyte completely separates the battery ends, yet its atomic structure allows ions to slip through. Inside this matrix of crystalline order, ions travel in highly predictable, efficient straight lines. Because we've removed the flammable liquid, engineers can pack these battery cells incredibly close together without the risk of thermal runaway. This creates a massive leap in energy density, the total amount of power stored in a specific volume. By swapping fluid chaos for solid order, battery packs can hold significantly more power in a much smaller physical footprint. This rigid structure also solves the biggest physical threat to a battery's lifespan, the dendrite. In liquid batteries, lithium forms spiky, needle-like dendrites that grow across the fluid gap and puncture the internal barrier, causing a short circuit. But in a solid-state electrolyte filled with dense ceramic, a forming dendrite is instantly blocked and flattened against the impenetrable wall. With the risk of short circuits and overheating neutralized by this physical barrier, manufacturers can now push electrical current into the cell at much higher rates, resulting in drastically faster charging speeds. By simultaneously eliminating the fire risk and stopping physical degradation in its tracks, this solid microarchitecture proves itself as the logical successor to the lithium-ion era. The chemistry works, but moving from perfect theoretical science to the harsh reality of industrial mass production introduces a completely new set of obstacles. Assembling solid-state cells requires extreme environmental control. The manufacturing lines demand perfectly moisture-free cleanrooms and immense physical pressures to ensure the solid layers bond correctly. It is one thing to engineer a single, flawless battery inside a pristine laboratory with an unlimited budget. It is a massive economic leap to profitably stamp out millions of them in a global gigafactory. The delay in solid-state adoption is no longer a question of chemical discovery. The challenge now rests entirely on mechanical engineering and global supply chain scaling. That scaling hurdle has triggered a global race. Legacy automakers, tech giants, and agile startups are all pouring billions into commercializing this technology first, knowing the winner will capture the market. If manufacturers can successfully produce these cells at a competitive price, they remove the range and refueling speed disadvantages that have long protected the internal combustion engine's market share. Scaling this architecture shifts the limits of our energy storage. It replaces 30 years of liquid-based constraints with a more stable, energy-dense foundation for our electronics and our transport networks.